Welcome to the course on Biostatistics and Design of Experiments. We will continue on Anova. As I said, Anova is the most important topic in the entire statistics. We can compare different operators, different process conditions, different drugs, and we can compare one way, two way, three way, multi way and so on actually. So, it is a very powerful tool and it is widely used tool. Okay. We were yesterday talking about something called replication. So, what is replication? Replication, we completely repeat the experimental run. That means suppose I am doing an experiment at pH is equal to 3, temperature is equal to 30 with the 1% inoculum size and some amount of carbon nitrogen. So, I complete the whole experiment, I get the biomass, I get the product metabolites. Now, I again repeat the same experiment with all these conditions and complete the whole experiment, get the biomass and the metabolites. That is called the replication. So, there is a difference between replication and repeat measurements. What is repeat measurements? Suppose I am running a fermenter, I take a sample out and look at the biomass by measuring the OD. Again I take a sample out and measure the OD. Again I may take a sample out, measure the OD, or I may measure the OD 3 times. That is called repeat measurements, but that is not completely repeating the entire experiment from the beginning with all the variables. That is called replication. So, there is a difference between replication and repeated measurements of the same material. So, I may repeat the measurement. Suppose I am measuring pH, I may do it 3 times, 4 times, 5 times. If I am measuring the OD to measure the biomass, I may do the OD measurement 3 times, 4 times, 5 times, right. So, that is called repeated measurements. That is not replication. So, in replication you completely carry out the reaction once more with all the conditions, okay, with all state variables or independent variables, complete the experiment and measure all the output variables or dependent variables. That is called replication. Okay. Replication is very important because when we carry out the same experiment completely twice, thrice, 4 times, we get a measure of the error that is involved in the entire process. So, the process may contain preparing the inoculum, adding the inoculum to the reactor, carrying out the fermentation, taking out samples, measuring the amount of metabolites by extraction, measuring the amount of biomass by centrifugation. So, it gives you a very good measure of error. And as you know, in Anova the error sum of squares is very important. That comes in the denominator when we are calculating F ratio. As you know, between sum of squares, that means between various groups divided by error sum of squares. So, error sum of squares is a measure of the repeatability of my entire process. It is not repeat but replication of the entire process, and that is very important to know in order to see whether there is any difference when I change temperatures or when I change pH or when I change RPM or when I change amount of carbon or when I change nitrogen and so on actually. Okay. So, replication becomes very important. Replication also adds to the number of degrees of freedom, and as you know, degrees of freedom are very important if you want to perform the Anova calculation. Okay. So, repeatability is measuring the same parameter twice, thrice, like if I am measuring pH, I measure it many times. If I am measuring temperature, I measure it many times. If I am measuring OD, I measure it many times. That is called the repeatability. Whereas reproducibility, I perform the entire experiment, okay. That is almost like that is the replication. So, reproducibility is very different from repeatability. So, I may perform the whole experiment from start, keeping all the independent variables and performing the entire experiment, or I may ask another operator to perform the experiment, assuming there is no difference between the operators. Okay. So, that is called reproducibility. Okay. So, reproducibility is same as replication, whereas repeatability is the repeatability of your measurement. Okay. Both are different. So, suppose there are 3 operators and they perform some experiments. We are trying to look at what is the reproducibility of these 3 operators. So, 1 and 2 may fall very closely, whereas 3 may fall away. Okay. So, that is called the reproducibility. So, both are different, repeatability and reproducibility, and as I said, replication is the same as reproducibility. Okay. These are terms you need to remember in statistics. Statistics has a lot of terms which cannot be used very loosely, although we keep using many words very loosely. In statistics we can't do that actually. Okay. Now, when we have more than one variable, say 2 variables, 3 variables, 4 variables, okay, you may have a situation where they could be interacting with each other. For example, suppose I am changing pH and I am changing temperature and running a fermentation process and measuring the product yield. Okay. At pH is equal to 3.5 I change temperature, so the yield keeps going up like this. Now at pH is equal to 4 again I perform experiments by changing temperature, again the yield goes up like this. Okay. So it looks like an additive, right. So I could develop a simple regression model. We will talk about regression much more in detail later. So I could develop a regression model like this, some constant plus A into x1, x1 could be temperature, B into x2, x2 could be pH plus some error. Okay. So these two parameters x1, x2, which are called the independent variables, in this particular case pH and temperature, they seem to be independent of each other. So they are adding to each other. So there is no interaction. Okay. But on the contrary, you could have situation like this, where at pH is equal to 3.5 you are changing temperature, your product yield goes up, but at pH is equal to 4 your product yield does not go up in the same way, it goes up and almost remains same, right. So there is a interaction, there is an interaction between pH and temperature. So the performance of the fermentation process seem to be not linearly changing with temperature, but it also depends on at what pH you are running at. Okay. So at pH is equal to 3.5 you are having like this, whereas at pH is equal to 4 it is not going up in the same fashion, but it seems to be sort of falling down. Okay. So there is an interaction between pH and temperature. So if you want to develop a simple linear regression model in this particular case, what will you have? You may have a constant plus Ax1, that could be temperature, Bx2, x2 could be pH, and also there could be a relationship equation which has d into x1 and x2. Okay. So x1 could be temperature, x2 could be pH. So obviously they are interacting here, a, b, c, d are constants here. Okay. So on the contrary to the previous equation where we have Ax1 plus Bx2, so they seem to be additive. So the effect of temperature, effect of pH are additive towards yield, whereas in this particular equation they are, you have a additive term plus also you have a interacting term between these two independent variables. So you may have like this, understand, or you may also have like this, at pH is equal to 3.5 as I change temperature product yield goes up, but at pH is equal to 4 when I change temperature product yield goes up very drastically. Okay. So you see each one of these curves, okay, these are almost parallel, so this is more like additive, these sort of converging, and these are diverging tremendously. Again you could develop a regression relation of this form where you say y is equal to some constant plus Ax1 plus Bx2 plus d into the product of these two independent variables. So here again we can say pH is interacting with temperature. Interactions are very common, especially in drug discovery. You are testing some drugs on a Caucasian population vis-a-vis African population, they may perform very differently. If you are testing some drugs with the Asian and Chinese and the Americans, the drug may be performing differently. Okay, so it is well known because of the genetic makeup of the people from different continents, drugs may be acting on different pathways and different genes, and hence they may be performing very differently. A drug which may be very active in some part of the world, in some part of the population, may be even toxic or detrimental in some other part. They are called interaction, and that is why nowadays most of the clinical trials are carried out in multi country or multi-continent, so that you get you are able to capture this type of effect. Suppose you carry out clinical trial only in say Europe, and you try to extend this drug in market it in Asia or Africa, you could get into trouble, because the drug may be acting very differently on the other type of population as against the European population. So that is called interaction, and it is very important to know interaction, because it is very common. As I showed you in the fermentation example, drug discovery, it is very common. In many situations you will find this type of problems. For example, some drug may work in one way on male population, whereas it may work in a different way on female population. Some drugs may work differently on infants as against on aged people. Okay, so these type of things are called interactions. The way some food works on aged people as against adult people, and so on actually. Okay, that is called interaction, and in statistics using Anova we will be able to find out some these interaction effects also. Okay, so let us look at this problem. So you have two drugs. I think you remember we saw this problem in the previous class. So we have two drugs, drug X and drug Y. It is supposed to be lowering the lipid levels. Okay, on the adult it is lowering little bit drug X, on old people it is lowering a large amount. Okay, when you take drug Y, drug X is increasing little bit on the infant, it is lowering on drug Y when drug Y is given, and it is almost constant on the aged people. So obviously there appears to be an interaction between drug and the age of the subjects or age of the volunteers. Okay, now let us look at the various degrees of freedom. Now there are 6 data points, so you have 5 degrees of freedom, right, 6 minus 1. Now age, there are 3 groups, so obviously 2 degrees of freedom. Drug is 1 degree of freedom, because you have 2 drugs. So if you want to look at age into drug, that is interaction, then you need to multiply 2 into 1, that comes to 2. So if I add this 2 age, if I add this 1 drug, and if I add this age drug interaction 2, they all add up to 5. Okay, so 5 minus 5 is what error will be. Okay, so obviously we cannot use this data set to find out interaction. Okay, so we can use this data set to find out effect of age, main effect, we will call it effect of drug, main effect. So 2 plus 1 is 3, 5 minus 3 is 2, and we will call 2 degrees of freedom for error. But if you want to bring in interaction age into drug, then error will have only 0 degrees of freedom, so we cannot solve this problem. So what does that mean? Okay, it means we have insufficient experimental data points. That means the degrees of freedom is 0, so we need to have more data points. That means we should have done a replication of all these. Okay, so if we had a set of replicates, then obviously we will have more degrees of freedom for error. In fact, the next example, look at this next example. So you have taken 2 infants and carried out this experiment, you took 2 adults, carried out 2 aged people. So now you have 12 data points, that means you have totally 11 degrees of freedom. Okay. Now age wise 3 age groups, so you have 2 degrees of freedom. Drug wise you have 2 drugs, so 1 degree of freedom. So age in the drug is 2, so 2 plus 2 plus 1 is 5, so 11 minus 5 will be 6 degrees of freedom for error. So we will be able to determine the sum of squares of error, and we can also determine the mean sum of squares of error, because how do you calculate mean? You divide by the degrees of freedom. So in this particular problem we can calculate both interaction and error, because we have enough data points, whereas in the previous case what happened, the error degrees of freedom was 0 if you want to calculate interaction. So what we did, we said we will not calculate interaction, so the error degrees of freedom will become 2, so we can calculate only the main effects. So now I am introducing another term, that is called main effect. Main effect in this particular problem is drug and age. The interaction effect is drug into age, then you have error. Okay, so in this problem also main effect is drug, and age is another main effect. The interaction effect is drug into age. So, in this particular case where we have 12 experiments performed, that means we have replicates here in each of the case. So, we have 11 degrees of freedom. So, there is no problem. Age is 2 degrees of freedom, drug is 1 degree of freedom, age into drug, you multiply this by this. So, get 2 degrees of freedom. So, they all add up to 5, 11 minus 5 is 6 error degrees of freedom. So, we can determine what is the error sum of squares, then we can determine what is the mean error sum of squares, then we can determine the f for the interaction also. You understand? Okay. Let us look at problems using interactions also, because as I said, interaction is very, very important. So, what does this mean? It means that replication is very, very essential if you want to look at interactions, if you want to look at errors and so on, because you need to have sufficient degrees of freedom, because error is what we use, the mean sum of squares of error is what we use for dividing the other sum, the group sum of squares to get the f value. Okay. Let us look at this problem. This a two-way ANOVA with replications, and also we are trying to study interaction. So, we have 10 volunteers, we have 5 male, okay, who were given a drug called metformin. You all know what is metformin, it is meant for lowering glucose, and you had another 5 male volunteers given another glucose controlling drug THZ. Similarly, you had 5 female volunteers who were given metformin, and you had 5 more female volunteers who were given THZ. Now, the question is there a statistically significant difference between drugs? You know how to do it, very simple. Is there a statistically significant difference between the sexes or the genders? Is there a statistically significant difference between the way these drugs act with each other? That is very interesting. So, that means there may be some interaction. So, how do you do this? For example, if I take an average of all these, because I have replicated with 5 males, I take an average of all these. So, it may come up to around 16 point something. Okay, for metformin male here, if I take average of all these, okay, so this may come to around that is male THZ, that may come around 19, that is here. Now, if I take average of all the female on metformin, these numbers are really large, right. So, you will get around almost 21, 22 and so on actually. Okay. So, sorry, metformin is here. So, if you take the average of all these, it may come to almost 35 here, and if you take average of all the THZ, you may get around 21, that is here. So, when you plot the average, these 5 values, average of this, average of this, average of this into 2 graphs, okay. So, this red indicates THZ, that is this and this, average of this and average of this, and here it indicates male, here it indicates female. Look at metformin, it is going like this. THZ is going like this. Obviously, there is an interaction. If you remember the old pictures I showed you, ideally if they are parallel to each other, we can say both the drugs act in the similar way between both the genders. But in this particular case, both the drugs do not act in the same way with both the genders, because they are not really parallel, they are diverging. That means the metformin is acting much more on female when compared to male, whereas THZ is acting only marginally on female when compared to male. So, it is because it is diverging, right. So, obviously there is an interaction, and we are interested in knowing the interaction. There are many drugs which have such effects. They may act differently on female and they may act differently on male. Okay. Let us go back to our usual ANOVA table and look at the problem. So, we write down the male data for metformin, male data for THZ, and then we have the female data for metformin and female data. Okay. So, male, this particular average, okay. So, if I take the entire male average 15, 18, 26, 14, 19 whole lot, I will get 17.2. That means irrespective of whether it is metformin or THZ, 10 data points. Similarly, if I take all the 10, I will get the female average 27.8. Okay. Now, if I add up all these, okay, and if I add up all these, and then I get this is called the drug average. Okay. This is for metformin, this is for the THZ, you understand, okay. This is for the metformin. So, just like male average, there is male average, I take all these 10 data points to get 17.2, female average I take all these 10 data points and get the female average, drug average I add all the metformin and take 10 divide by 10, all the THZ and divide by 10. Okay, now the grand average will be average of these two or average of these two. This is the grand average. Okay. Now, how do you get each of these sum of squares? Okay. So, we have the male average 17.2, female average 27.2. So, how do you get the gender sum of squares? Simple. This is the male average 17.2 minus 22.5 square into 10, because there are 10 data sets here. Okay. So, and then similarly for the female, what do you do? 27.8 minus 22.5 square into 10, because then there are 10 data points. Do you understand this? Okay. So, we take the male average, all these 10 data points, female average all these, overall grand average is this. So, for gender you 10 into this minus this square plus 10 into this minus this square, okay. Then if you add up you get 561.8, that will be called the gender sum of squares, okay. Now, how do we do for the drug? Okay, so we have the drug average here 26.7 minus 22.5, that is the grand average, x double bar if you remember, square 10, because there are 10 points here, right. And then same thing 18.3 minus 22.5 square into 10, then you add up these two, you will get 352.8, that is called the drug sum of squares. Okay. So, you got gender sum of squares, we got drug sum of squares. How do you get the total sum of squares? You all know, right. 15 minus 22.5 square, then 14 minus 22.5 square, 18 minus 22.5, like that. All the 10 data points we do like that. So, how do you get this? 29 minus 22.5 square, how do you 49 minus 22.5 square, like that. So, if you add up all these, you will get the total sum of squares. So, you know how to do total sum of squares, you know how to do drug sum of squares, you know how to gender sum of squares. Now, error, how do you get the error sum of squares? Okay. Error, okay. So, this is 18.4, that is the column average, okay. Now, this is 17.2 is the overall average, okay. 17.2 minus 18.4 square, okay, into 5, because there are 5 data points here, that is called the error sum of squares. Okay. And similarly we can do for the other one also, we will get 29 minus 35 square, okay, 35 minus 27.8 square into 5, okay. So, like that you keep on doing. Then again for this 16 minus 17.2 square multiplied by 5. So, that if you add up all these, that will give you the error sum of squares. So, the error sum of squares, so we know the grand average, we know the gender sum of squares, we know the drug sum of squares, we know the total sum of squares. So, the error sum of squares is also known. So, if I subtract error sum of squares, drug sum of squares, gender sum of squares, I should be able to get the interaction sum of squares. Do you understand? So, we go to Anova table. So, we have the gender sum of squares 561.8, drug 352.8, total is 1627, 533 is error, okay, and then error gender into drug, that is the interaction. You add these terms and subtract from 1627. Okay. Now, in total we have 20 data points. So, 20 minus 1 will give you 19 degrees of freedom for total. Gender, there are 2 genders, male and female, so DF is 1. Drug, we have 2 drugs, so DF is 1. Gender into drug is 1. So, error is 19 minus 3 is 16. Okay. So, mean sum of squares, what I do, I just divide with the DF. So, I will get 561.8 as the gender mean sum of squares, 352.8 as the drug sum of squares, gender into drug as 180, and of course, the error is there actually. Now, error is 532 divided by 1633. Now, how do you calculate F for gender? This divided by error. How do you calculate for drug? This divided by 33, gender into drug 180 divided by 33. Okay. Now, let us go to F table for 1 and 16 degrees of freedom, 4.49 at 95%, okay, 4.49. Okay. So, at 95% confidence, all these 3 are significant. That means there is a significant difference, the way the drug acts on gender, the way the performance of the 2 drugs, and there appears to be a gender into drug interaction. At 99% confidence interval for 1 into 16, okay, for 1 comma 16 is 8.53. So, only gender and drug become significant, and the gender into drug, which is called interaction, is not at all significant. Okay. But at 95% it is significant at 99, and as I showed you here in this picture. So, if you look at THZ, male it performs in certain fashion, female it performs, there is an increase, whereas if we take metformin, male it performs, but in female there is a very drastic increase. Okay. It is not like this type of increase with this slope, but the slope is very, very high. So, if you come across such a situation, we can very confidently tell that there is a interaction between the way the drug responds on male as against on female. Otherwise, if there is no interaction, you should get approximately a parallel line, understand. So, this is a very important problem where you are looking at a 2A ANOVA with replication to study interaction. So, the main point is you need to have replication of the data here, that is very, very important. Okay. You need to have replication of this data, otherwise as I showed in one simple example, if you do not replicate, there are no degree, if you take interaction, then there are no degrees of freedom for error. So, if you consider error, then we cannot measure the interaction effect. So, we will continue further on this ANOVA with replication and interaction in the next class. Thank you very much.